Bueno, pues buenos días a todos. Una vez más vamos a empezar el seminario junior del Instituto Gregorio Millán Marvani. Hoy ya por fin hemos conseguido este aula, que llevamos tiempo detrás de ella y siempre nos la habían quitado. Los siguientes seguramente vuelvan a ser en las otras aulas porque esta está reservada. Y ¿el siguiente también es aquí? Ah, pues mira qué bien. El siguiente también es aquí, perdona. Y bueno, hoy tenemos a SERGEI, que de hecho es mi compañero de despacho. Él está haciendo la tesis aquí en la Carlos III y bueno, no sé si nos vas a hablar exactamente de tu tesis, pero nos va a hablar de cómo se vive en Matrix, hablando de matrices muy grandes. Muchas gracias.
Hi. Yes, I will be talking today about system of linear equations and about matrices. And from the beginning, it seems that we know a lot about matrices and we know a lot of different algorithms how to solve systems. However, in a lot of industrial and scientific application, it's almost impossible to apply the known algorithms like Gauss elimination. And therefore, people use another methods, and I will speak about these methods today. So, at the beginning, I start to think from which age in what age we first faced matrix the first time. And I found these kind of problems, which are supposed to be solved by children in 10 years or something like that. So they don't know matrices at all. And so they have to invent, it's like advanced problem, and they have to invent their own method to solve them. And so in this case, probably the author of this problem thought that the boy or a girl should assume that if we buy two first collections of hats and scarves, then we obtain 6 scarves and 4 hats, and you can note that number of hats is similar, and the difference is only in scarves and in prices. So from that we can note that 5 scarves cost 15 euros, and therefore 1 scarf 3, and a hat 5. So here, as you can see, we don't deal with some unknown variables, and even with rational numbers, we only use natural numbers. And so when people start to study system in school, they can already become like less creative and formalize everything without pictures, but with x's and y's. And here we consider the system as 2 equations, and we try to reduce it to known 1 equation. So we try to eliminate 1 variable. And here we already start to use rational numbers. And well, for 10 years old child, probably it's hard to imagine that he or she can pay for a scarf 19/3 euros, and also they will obtain 2/3 of a hat. It's the kind of nonsense. And in university, we got more lazy and even more abstract, and we can write it in matrix form, where A is operator with known coefficients, X is vector from Rn, and B is the right-hand side vector with 19 and 23. And here, instead of considering it as 2 equations, we can consider operator A as an entire object. And therefore, if we guess 1 solution, we can use properties of this object, particularly that this matrix is not singular, its determinant is not 0. And therefore, the system always has only 1 solution, which we already guessed. So, and all these kind of problems in the web page I found it called Systems in Real Life, but I suppose it's actually not Systems in Real Life because, well, it even doesn't look like some crazy Black Friday offer. And in real life, in real application, people consider system usually related to optimization problem and to numerical simulations or for some statistical problems. And we will stop on numerical simulation because it seems that, well, because I do numerical simulation in my PhD project, in my PhD thesis, and also because I think it's simpler to derive matrix equation from some physical problems than from optimization problem, for example. So consider this physical problem of oscillation of a string, And if we want to simulate it on a computer or even by hands, we probably will use the naive approach. We divide the system as a set of masses connected by springs and apply Newton's law for each mass. So we obtain that mass multiplied by second derivative equals force from the spring on one side and plus force from spring on another side. And if we group everything, we obtain that thing, this expression. And after calculating of coefficients respect to properties of spring, so in this case, stiffness of spring can be calculated as stiffness of all system multiplied by number of nodes. Mass is mass of all string divided by number of nodes, obviously, and number of nodes can be calculated as length of all spring divided by this step size, as the length of connectors h. And if we do it, we obtain this kind of system. And if you are familiar with finite difference, you can note that this expression is exactly finite difference approximation for second derivative. And it also can be written in matrix form. And this matrix A can be very large because the better we want to approximate this physical process, the more masses we have to use. And on the other hand, there are a lot of zeros because in each row we have only 3 elements. So we have only 3 diagonals and all other elements equals to 0. And these properties are common for matrices which arise from numerical simulation. They usually are very big. They can contain millions. Their dimension can exceed millions. But there are only a few, only a small part of components of this matrix which are distinct from 0. And so why we have to solve system? Well, in this particular case, it's not necessary because we can use explicit times him. But if we wanted to use implicit, which probably we can, we would obtain that thing. So we approximate this second time derivative the same way as actually we approximate spatial derivative as vector on the new moment of time minus 2 vectors in the present moment and plus the vector on past moment and the previous moment. And if we will use Crank-Nicolson scheme, we have to set it equal to 1/2 of this term calculated on the current moment and the new moment. So it's average of the next moment of time and the previous one. And so now we have the only one unknown is xj plus 1, and we have it here and here. So to calculate it, we have to solve system of equation, which with matrix probably 1 divided by tau I minus a. Now imagine that if our matrix A dimension of matrix A goes to millions, and if we want to store this matrix in a very strange way, we are trying just to write it on a sheet of papers of A4 size, for example, and we are writing this matrix. Well, each component we will write with 5 or 10 digits to have a good precision, and we will collect all the sheet of papers in a tower. What do you think? How tall this tower will be? If it will be a size of meters or kilometers or thousands of kilometers? Well, actually, it will be thousands of kilometers. So it can be comparable with diameter of Earth, with radius of Earth, but also with diameter, because if we just increase matrix more times, 2 times, this matrix increase the number of elements increased 4 times. And so radius of Earth is 6,400 kilometers, I suppose, and so this matrix is more or less equivalent to this length. However, as I said in the previous slide, the matrix which are emerged in numerical simulations are usually sparse, and for this kind of matrix of millions elements, it means that only 1 million part, or this 0.0001% of matrix, is occupied by something distant from 0. And on this image, this part which is not 0 is equivalent as is the same height as a just very high building or a skyscraper. So actually, most of these sheet of papers are filled with zeros. And so therefore we don't have to store that thing in memory. We can store only this part and use only this part to perform any operations with matrix. And of course, it's quite hard to store all that in. Well, it's impossible to store it in sheet of papers, but even in computer memory, it's quite hard because it will be around terabytes. So it's possible to store it in hard drive, even so it's possible. But in RAM, it's quite complex. And to solve matrices, usually we have to upload it in RAM. Well, firstly, consider direct methods. So I already said about Gauss elimination at the very beginning, and we used some similar procedure for that children problem. But usually this method is not used in practice because it's numerically unstable, and the most popular method are based on different factorizations of initial matrix. For example, LU factorization. In this method, we decompose our matrix A into two matrices L and U, where L is lower triangular with unit diagonal, and U is upper triangular. And then we can calculate all coefficients of U and L by parsing through from left to right and from up to down in the resulting matrix. For example, firstly, we can calculate U11, which is equal to A11. So in that example, it was 3. Next, U12, which we can calculate 4, which is equals to 2. And on the second row, we have L21 multiplied by U11, which is equal to A21, but we already knew U11 from the first row. So the only one unknown is L21, and so for the last component, the only one unknown will be U22 because we have already calculated L21. And so because of this property, this algorithm is quite easy to implement in computer because actually you have to just implement one formula, and in this formula you always don't know only one coefficient and know all other coefficients. And so after you perform factorization, you have two triangular matrices, and system with triangular matrices can be solved easily, more or less the same way as we calculate these coefficients. For example, here, from the first row we calculate theta, and on the second row we don't know only one element eta because all previous elements we have already calculated. And so the same for upper triangle, we calculate the last element, and next we go up and calculate one more element for each row because all previous elements have been already calculated. And for example, in MATLAB, if you use MATLAB, you probably know about backslash operator, which is used there to calculate to solve system or calculate inverse matrices. And this operator actually check a lot of properties about matrix. For example, is it diagonal, is it tri-diagonal, is it triangular or symmetric? But if answer is no for all these questions, then this operator performs LU factorization. So this method is sort of the biggest gun which MATLAB used against systems when all other weapons have failed. Another popular algorithm is QR factorization, and here we decompose A as a multiplication of orthogonal matrix, but for square matrix means that its inverse equals to its the transpose, and upper triangular matrix. There are a few approaches how to calculate this matrices Q, but so we consider one of them, which based on Given's rotation, means that Q is a multiplication of a lot of rotations matrix. So for our 1D case, we need only one rotation, and so this matrix calls rotation matrix because if we apply it in 2D space, we will rotate on space to angle alpha. And so if inverse of this matrix, of course, rotation to angle minus alpha, and if you plug minus alpha instead of alpha here, the cosine will be the same, and sine will change its sign. So we obtain exactly a transpose matrix. And here R is given as QT multiplied by A, and we can choose sine and cosine of alpha that way that make these coefficients 0 and make R indeed upper triangular. So it's possible to do in any way except when both these coefficients are 0, but in this case, A was already been upper triangular. So usually QR factorization is used when we have to transform, so multiply by this matrix Q, not only the matrix A, but also some another matrices or another vectors. And it is simpler to parallelize than LU factorization. So what's the main problems with direct methods? Firstly, that direct methods always perform O of n cube operations. So O of n cube means that we don't know exact constant, but so we can estimate number of operation as a sum constant multiplied by n cube. But how with this constant, it's not necessary to find. And so that in direct methods it's quite hard to take advantage of matrix structure, because even if it's sparse or block or has block structure, the method will work the same way. And the main disadvantage is that direct method also find an inverse matrix, which we not usually need. And inverse matrix is usually full populated, what means that we have to store all this tower of sheet of papers from the center of Earth to the surface. And it's just impossible to do for matrices which size million. And it's quite a pity that this method used this O of n square memory to calculate things which we actually don't need. We don't need the inverse matrix. We need only the solution of system. And another small disadvantage is that we need direct access to matrix element, which is not, which could be not easy because matrix can be given as a formula, or if it has sparse structure, then usually each row is represented as a list, and to have access to the last element in list, we have to pass through all previous elements. So it can be more complex than, for example, for matrices which is stored is a one block in computer memory. Actually, there are few curious facts about finding inverse matrices, which looks quite counterintuitive. And so I said that we need n of n cube operation, but actually it's not true. We can do it faster. And so it looks quite strange, but so firstly, it can be proved that the finding inverse matrix has the same complexity as a multiplication by two matrices of square matrices of size n. So it means that if somebody gives us a subroutine which calculates matrix multiplication, we can use this subroutine to write our own procedure to calculate inverse matrix using only that subroutine and few simpler operations. And on the contrary, if we can calculate inverse matrix, we can use it to calculate matrix multiplication. And the second factor, which is also quite curious, is that we can multiply square matrices faster than n cube. So in university, we usually calculate matrix multiplication for each element as a multiplication of row. So each element is given a scalar multiplication of row of first matrix and column of the second one. So to calculate scalar multiplication, we have to perform n operations, and we have n square elements, so finally we have n cube. But it's possible to create algorithms which will do it faster. For example, Strassen algorithm, which do it in n in power logarithm 7 on base 2 operations, which is smaller than 3, because if it were 8 here, it would be 3, and here it's smaller than 3. And so this results, so people knew about matrix for a long time, but these results are actually quite recent, because so it only 15 years when people start to find more efficient algorithms for matrix multiplication. And now the best result that we can multiply matrices in power n in power 2.4 approximately operations. And the lower bound for this algorithm, for that kind of algorithms, is still unknown. So we know exactly the lower bound, that we can't multiply matrices faster than O of n square, because we have to write the answer, and to write it, we need to perform O of n square operations. but something, is it exact or is it another lower bound? We don't know. So it was just a small remark about finding inverse matrix. But we are looking not for inverse matrix and for solution of system. And since we cannot apply direct methods, we will use we have to develop another methods. So firstly, we of course we don't want to find inverse matrix. We only want to solve system. It also would be great if we could use matrix structure to use some knowledge about this matrix. For example, this is this matrix is approximation of some differential operator, and so the main idea is that we will consider this system not as a set of different equations, but as an operator equation. What means that we consider A as an operator or as a mapping from axis to B, and basically it means that A is all the arrows which pass from X to B, and we want to find arrow which ends in this element B. It means solve the system. And so when we calculate inverse matrix, we try to calculate all arrows which goes back, and of course it's a more complex problem. And now we just want to pass through some arrows and try to find the best one, or well, trying to find the exact one, or at least the best one in some sense. So we can do it by reducing our sets to smaller and find the best approximation in that smaller subsets. And next we can continue and find another best approximation, best in some sense we will discuss later, and so on. So that's basic idea how we are going to develop our method. Now we can consider this applied to the simple 2D example. If A is only matrix 2 by 2 and is symmetric and positive definite, and can be considered, so solving a system can be considered as a solving of this optimization problem, because if we calculate gradient of this functional J, we will obtain exactly system of AX equals B. So level lines of this function can be ellipse. So the lowest ones are close to the center. So here we have a solution, the optimal point and solution of system, and far from center we have large values of J. So let's start from some point x0 and select first subset, or in this case subspace. We select that first blue circle from the previous slide, and in this case it is a line defined by vector v, and so initial vector v0. So we look only for x's, which could be written as a x0 plus alpha v, where alpha is a number, and we find best candidate on this line. And obviously the best candidate is this point, because it's solution of reduced optimization problem, and because gradient there has the smallest norm and is orthogonal to the defined subspace. And this gradient can be, so minus gradient actually is equals to b minus x ax, and for numerical methods for systems, this vector calls residual and represent error which we have when we solve system, because if we plug exact solution here, we obtain 0, and if we plug something close to exact solution, we obtain some very close value close to 0. So if norm of this expression is small, it means it can be considered as that error is small, and it means that this x is a good approximation of the final solution. So next we have to move from this one-dimensional subspace to two-dimensional subspace, and probably we will move in that direction and find the exact solution. So how to implement it in general case for n dimensions and for non-symmetric matrices? So firstly, we define two subspaces. First one will be, we will call search subspace, and from there we will pick candidates for solutions. So on previous slide it was that dashed line x0 plus alpha v. And secondly, we define subspace of constraints, which is needed in order to reduce a problem has a solution. And at each step, we will solve these problems, that we choose x from x0 plus z subspace k, such that has a residual vector, has arrow orthogonal to Lm, which means that this arrow is outside the subspace of constraint. Or in other words, that on this subspace L, we have zero error, so it means that we solve system on at least there, at least in small subspace. So if we want to write it in matrix form, we define two bases for K and L. For K we use V, and this matrix V is has all columns equals to basis vectors V1, V2, and so on, and the same for double V. And this reduced problem is equivalent to these two equations, that x is given as x0 plus some linear combinations of vector v, can be written as vm multiplied by y, where y is coefficients, vector of coefficients, and double v and r should be orthogonal to all vectors double v, because it should be orthogonal to all subspace L. So, and if we plug expression for r, we obtain the system, and we can already see advantage of this method, because this system contains only n equations, and so if solution of the system gives us exact solution of the initial system, it means that we reduced our problem from millions to probably hundreds or thousands, and so it's possible to solve this system in any direct method. So it's the basic idea of iterative methods, which called projection methods, and so it's general recipe, and we can choose our own ingredients as K, L, and this basis to develop our own method. So it means that we have to choose which K and L we will use, what is search subspace and what is constraint, subspace of constraint. We have to specify how we will calculate these bases v and double v. Will they be orthogonal, or we choose any vectors, and how we are going to solve the system, which method we will use, and how the system will look like depending on matrices v and double v. So for the first question, actually basic iterative methods as Jacobi and Gauss-Seidel use another subspaces, but the most popular use Krylov subspaces, which was proposed by Alexei Krylov. And well, actually I can put photos of a lot of people in this talk, because we speak about a lot of different matrices and different methods, but probably so actually methods based on Krylov subspaces as the main topic of this talk, and therefore I decided to put a photo of Alexei Krylov as a protagonist of this talk. So, and also I had space on this slide, so and on the other I didn't. And so Krylov subspaces is a linear span of this vector R0, A multiplied by A0, and all other powers of A multiplied by R0 until power m minus 1. So it's subspace of dimension m. So sorry, it should be m here, not m1. And it means that vector x can be represented as x0 plus linear combination of these vectors from linear span. And in other words, that it can be written as some polynomial of matrix A, because we have different powers of matrix A, including 0, which equals 1, y, multiplied by the residual vector R0. Or it means that we can represent inverse matrix. We try to express inverse matrix as a polynomial of initial matrices. So which can be so actually it's usually a good idea to express something we don't know as a polynomial of things we already know. We use it a lot in math. And so since we have to choose two subspaces K and L, we can use two different approaches. If A is positive definite, we usually choose same subspaces. equals the Krylov subspace of calculated in initial residual R0 and A. And if A is not positive definite, we choose different subspace of constraint, which is equal A multiplied by the search subspace. So we shift all these vectors to the left and add one vector more. Now, how to calculate the basis in Z subspaces? So we will use orthogonal normalized basis because everything becomes much simpler when bases are orthogonal and normalized. And so first vector we choose R0, but we have to normalize it, so we divide it by its norm. And next, for any new vector, which is given as A multiplied by the previous vector, because all Krylov subspaces can be generated from the first vector. Next we multiply by A, next we again multiply by A, and so on. So and we obtain this set of different vectors. So we start from this vector A Vj, but it can be not orthogonal to all previous vectors. So we have to orthogonalize it, and in order to do it, we just subtract from this vector scalar multiplication of itself with with other basis vectors multiplied by that vectors itself. So finally, if you calculate scalar multiplication after this procedure of Vj plus 1 and Vi, you will have here in the previous value. So here you will have this Hij, which is equals to A Vj multiplied by Vi, and at the beginning you had the same coefficients. So these two values will cancel. And finally we normalize the obtained vector. And all these coefficients H we are going to store in matrix H, which will be Hessenberg matrix, which means that it is almost triangular. So here we have all elements in this triangle, but apart we have one diagonal. And also it is rectangular because it has m columns and m plus 1 rows, and the final row we have only one element, which equals to this exact norm. So this algorithm is quite famous, but unfortunately it can be used in practice because it's unstable. Actually, this algorithm can't perform even 20 or 30 operations on real matrices of size, well, even on matrices on size thousands, with dimension 1000, it will disconverge after 20 or 30 iterations. And therefore we have to use modified Gram-Schmidt algorithm, where the main difference that when we calculate scalar multiplication, instead of initial prediction A Vj, we use the current value double Vj. So here we start the same way, and next we update and use already updated value here. And it leads to more stable procedure, but even in case that if even that thing blow up, we can use orthogonalization, what means that we calculate initial norm of Vj and calculate final norm. And if it decreased a lot, then probably it means that Vj is kind of linearly dependent on the previous vectors, and is orthogonal not because it's indeed orthogonal, but because it's close to 0. So that we, after this subtraction, we cancel all components of Vj, and finally, yes, of course, it's orthogonal, but because it's just very small. And so, if norm has decreased a lot, we start orthogonalization again, and stop only when the norm at the beginning is more or less the same as norm at the end. So it means that we already have vector which goes outside to the previous subspace. So now we can write this method in more details. So we start from point x0, calculate initial residual. Next we select subspaces according to that rule that if matrix has general shape, we choose for search subspace Krylov subspace of already normalized vector R0 divided by beta. And for subspace of constraint, we have to shift it by one matrix A to the left. And now we have to implement this orthogonality condition. And to do it, we can use properties of vectors, of basis vectors Vi. So if we multiply A by Vm, it can be written as multiplication of A by all basis vectors. And we can perform a procedure which is inverse to the Gram-Schmidt orthogonalization, because in Gram-Schmidt orthogonalization we started by this vector and subtract all previous V's multiplied by corresponding coefficients to get V2. And now we can say that this vector is V2 plus all previous vectors multiplied by corresponding coefficients. And the same with that thing. And finally we have this sum. And it means that this matrix is equal to this matrix Vm plus 1 multiplied by Hessenberg matrix we obtained at the previous slide. So probably it's the most complex part of the method. And now, if we calculate multiplication of double V, which in this case is A Vm by residual vector, we can note that this R0 is beta V1 because we choose V1 equals normalized residual. And here we can apply 2 times these properties, and vectors V and Vt will cancel because we have orthogonalized basis, and we end up with this problem, which is equivalent to minimization of this norm. Because if you write this norm as a scalar multiplication of this vector transpose by itself, and next calculate gradient, you obtain exactly this expression. And so this norm is norm of residual, and therefore at each iteration we try to minimize residual, so minimize our error as basically as we did on the very beginning when we considered these z ellipses. And so from this problem, this method has a name. It's called generalized minimal residual method because it works in general case, and it minimizes residual at each step. So the algorithm, the complete algorithm looks like this, like that. So we perform modified Gram-Schmidt orthogonalization m times, and next just solve this problem we obtain. And there are 2 questions. First, that if we have to perform a lot of steps, if m is very large, if we don't obtain good approximation after 100 or 1,000 or 10,000 steps, we have to store all these v's and all h in memory. And if m tends to n, it means that z matrices will be close to the initial one, which we couldn't store. And what to do in this case? And the second is that this method minimizes residual, but actually inside the main loop, it doesn't know the value of residual and value of solution, because solution and residual we calculate at the end. And probably it would be great if we had some approximation of residual norm inside this loop in order to exit from it before we perform all m operations. So the first problem about size of v and hm can be solved quite easily. First, that because this method is iterative, we can choose some value m, capital M, and restart method after this m iteration. So we have to store only m basis vectors, and h has size m, capital M by capital M plus 1 by capital M. And another possible solution is keep only m last vectors in V and orthogonalize everything only respect to those vectors. So this method is more complex to implement, and I suppose it also less stable and can diverge in some cases. And for the second thing, for the calculation of residual, we can use given rotation and use that matrix H is a Hessenberg matrix, what means that it's triangular with one diagonal, and only one rotation for each row will make this matrix completely triangular. And we can calculate the last components of y, which are the most important because usually residual is always orthogonal. We try to orthogonalize residual to the all previous subspaces. So as that first image of optimization of 2D problem, when we solve sub problem, we have our residuals only outside of subspace L, and probably they will be corresponding to the last vectors of Vm plus 1 of the basis vectors Vm. So we only need the last y's. So if we apply rotations, first rotation will change these two rows and two first elements of the right hand side vector, and in the end we rotate everything and have this vector fully populated. But we can use this last element as a residual norm, because if you will do these calculations exactly, you will find out that this absolute value of this element equals to residual norm, and therefore we have to calculate at each step only ZC. And to do it, so actually we just have to rotate this vector. So this rotation we can perform step by step. For example, when we calculate the first basis vector, we rotate this first column. When we calculate second, we rotate second column, and so on. So it means that inside our algorithms, this matrix H, so the initial matrix H, is always transformed to R and always maintain this triangular structure. And at each step, we have to rotate only the last column and the last components of this vector. So now we can try to use this method. So I found some matrix which probably comes from real numerical simulation. So it is stored in sparse matrix collection and probably corresponds to heat equation in some 3D domain. And in this simulation, so after used around 1.5 million nodes, and the reform matrix has size 1.5 million and 1.5 million. So it's in a paper storage, it will be around 1,000 kilometers tall. And so we can't use direct methods for this matrix, but we can apply our algorithm and plot the residual depending on iteration. And you can see that only after 10,000, well, 12,000 iterations, we already has residual quite small. So this it means that we perform it was 1,000 times less iterations than matrix size, and already obtain some convergence. And another interesting result is that at the beginning, residual falls quite fast. Next, it starts to fall slowly, and finally more slowly. And it's common for numerical methods. And it's not good because if we stay very close to solution, it's quite hard to improve our result. We have to perform a lot of iterations to get better approximation, even though we already have very good approximation. So yes, and this algorithm I launched for. I restarted GMRes every 100 iteration. So it perform 100 iteration, next start again, next another 100 iteration, and so on. And therefore, I have to store only 100 vectors of this size, which is possible to do for modern computers. One interesting modification is that if matrix is symmetric, we can get rid of using memory at all. Well, we use it only for some very simple things like vectors and constants, but not for matrices like Vm. And it is possible because if matrix A is symmetric, it means that matrix H also will be symmetric and still is Hessenberg matrix. So it means that it's triangular with one more diagonal, but since it's symmetric, it means that above the diagonal we have also only one line of elements. And so it means that H can be written as three diagonal matrix with coefficients alpha and beta. And also we can use another orthogonalization procedure which called Lancer. I suppose it reads like Lancer. And so in this procedure we use only last two vectors V to calculate new vector W orthogonal to all previous ones. So actually it happens because in each row of this matrix we have only three elements. So that elements corresponds to Z coefficients. And now instead of QR we can use LU factorization, which is more or less the same for symmetric matrices, but the advantage of using lower triangular matrix is that when we solve system with triangular matrix, with lower triangular matrix, we start from above and goes down. So we firstly calculate the first component and next all rest components. And for upper triangular, we move in opposite way. We calculate firstly last component and next update all the previous ones. It means that in new step, when new lines, new line and column, new row and column enter to matrix T, we have to recalculate last component of vector Y. And if last component of Y changes, it means that all previous components also change, because if we use upper triangular. But for lower triangular, it's not true, because because in this case we'll change only two last components. So in more details, that if we say that T is L multiplied by Q, and introduce a new vector Z which equals Q multiplied by Y, then we have a system for Z with lower triangular matrix. And so this Z we can update progressively, because in the first step we know the first Z, and the second step we have to calculate the last one using the first one, and next we have to calculate the third one using the all two previous ones, and so on. And so it means that we always know all vector Z with using relatively cheap computations. And X can be written in terms of Z as x0 plus double V multiplied by Z. Here double V is just V multiplied by Q, by Qt. And so it means that all previous vectors of Z we already know, and we can start to sum these vectors progressively in each iteration, and don't wait until we calculate we pass all M steps, obtain this matrix with double V, and calculate this vector Z. Because as I said, for lower triangular matrix, we always have to perform operations for the last two rows, and in each step only last two rows of this matrix and last two columns of double V change. And all previous part we can already sum up to the x0, and don't worry about that. So this algorithm is better than GMRS for symmetric matrix, because here we don't have to use any restart, and we don't have to store any large quantities of any large matrices. We just to perform quite similar operation in each step and wait until convergence. We can see that on the plot with residual, that speed of convergence decreased with number of iterations. Actually, it happens because numbers of step which iterative methods usually does depends on condition number of matrix. And condition number is ratio between the maximum eigenvalue and the minimum eigenvalue of that matrix. And for 2D, for example, if condition number is close to 1, it means that that these level lines for optimization problems represent circles. It means that size of this axis of ellipse and these sizes are equal. And if condition number is large, it means that our function has very long these level lines, and very long in this direction and very thin in the opposite one. And so if in this case we can calculate solution quite fast because we go there, and next we calculate orthogonal vector with a very high precision, then here we have a problem because we come here and it's hard to calculate good orthogonal direction, and therefore we start to oscillate here near solution, and so therefore we are very close to solution, but we can't improve it because this function looks like a plateau, and it's hard to find the beta point in this center, near this center. And there is a way how to there is a remedy for this problem, and it's called preconditioning, and it consists in solving preconditioned system, which is this matrix equals p minus 1 multiplied by a instead of the initial one. And this matrix P calls preconditional, and usually people try to choose precondition close to initial matrix A, but very easy to inverse. So it means that if we know something important about A, we can store it in preconditional and use it to speed up our method. One basic choice for preconditioners are diagonal preconditioners. So it actually, for symmetric positive definite matrix, diagonal is very close to matrix, because diagonal usually contains the largest element, and also they're larger than all other elements on the row. And so this matrix is easy to calculate, and easy to calculate inverse, because inverse of diagonal is just diagonal filled by inverse elements. Another common precondition is incomplete ALU factorization, which means that we perform ALU factorization but only for non-zero elements. So as a result, we complete something close to ALU factorization, but easy to calculate, because we store only the same amount of numbers that we had in the initial sparse matrix, and easy to calculate because we don't have to calculate a lot of elements, and also easy to inverse because these matrices are upper and lower triangular. And in this case, usually instead of multiplication by matrix P, people write system as two systems, where first is A multiplied by L from one side and Q from another side, L minus 1 and Q minus 1. And next solve another system with matrix U to get X from this vector Y. And especially for numerical methods of differential equations, one of the most efficient preconditioning method is multigrid preconditioner, which actually allows to solve system even faster than multiply by inverse matrix if we knew it. So it means that sometimes it seems that if we have to solve a lot of system with a similar matrix, probably it's better to calculate inverse if we can store it, and next just to multiply by this inverse. But with this method and with this preconditioner, it could be not true if matrix is very large. So that it's simpler to solve matrix, to solve system, than to multiply vector B by inverse matrix. And the idea of multigrid method is quite simple. That in numerical simulation, usually we discretize space. As we did, for example, for that string problem, we introduce masses connected by spring. And for 2D, usually we have, again, masses in these Z intersections and spring between them. And we can do a few discretization with lower numbers of nodes. So here we have a lot of nodes, here we have only 9, and here we have only 4. And next we choose some iterative methods and perform 3 iterations with basic matrix A1 on the first layer. And next we restrict obtained residual to the lower layer and use this restricted residual as a right-hand side vector for the solution on this layer, and perform another 3 iterations. and do the same with obtained residual. On the last layer, we have very small matrix, so and it's very easy to solve system. So probably solution of system on this layer will be simpler than one iteration on the highest layer. And when we obtain solution, we go back, we calculate a new vector x for the second layer as its previous value plus interpolation of obtained solution x3, and perform another 3 iteration and do the same for the first layer. And if here we are satisfied with obtained solution, then we stop. If not, we do the same thing once again and repeat it until convergence. Usually, this cycle actually calls V cycle because it looks like letter V, and usually we have to pass only few or maybe 10 or 20 times, even for very large systems. So it means that number of iteration for system of thousands and hundred thousands of elements required only, well, less than 100 iterations, which is quite fast. And the main question is how to calculate this operator of matrix I and R. So the I is quite easy to calculate because, for example, for this node, we can use some average value of all these 4 nodes, and for this, for example, average value of Z nodes, and so on. And for R is more complex because, for example, if we just say that value here is equal to value here, and the same for all corners, we will lose information from all these nodes, which is more than half of all mesh. And it actually presents the fact that R is not, if I is just calculation of of function we use as approximate solution, R is some integral characteristic and actually equals integral of that approximation along z square or probably along all z square. And it could be hard to obtain correct shape for matrix R, and because if in this case it is possible because we have well-structured mesh. But if mesh is not well structured, it contains a lot of triangles, or probably we have one mesh in triangles and another one in pentagons or squares. It's quite hard to find. It's easy to calculate matrix I, but it's very hard to calculate R. And therefore, people use just transpose of I for R multiplied by some coefficients, which is sort of normalization, because when we integrate, we have to sort of divide by area of the element or something like that. So I think for 1D solution, I'm finding difference. This alpha is 1/2, and for 2D, I suppose it's 1/14 or something like that. So, and to sum up what I have said today, is that direct methods are usually impossible to use for industrial applications and for scientific calculations when matrices are very large. And therefore, we have to use, and the basic problem is that they want to store inverse matrix and they can't work without this inverse matrix. And therefore, we have to use iterative method, which are looking for solution itself without any inverse matrices. However, for that methods, number of iterations usually depends on properties of matrix, especially of condition number, and we have to use preconditioning technique to reduce that number and obtain more efficient method. And in other words, there is no one recipe for all problems. For some complex matrices, you have to invent to make some research and invent your own method and at least your own preconditioner to obtain solution fast. Yes, and also I would like to say that, well, for this talk I actually use this book of Saad, which is quite useful for iterative method for linear systems, and also one paper about, well, I use more things, but basically this talk was constructed on chapters of that book. And that's all.
Bueno, muchas gracias, Sergei, por la charla. Bueno, no sé si tenéis alguna pregunta, alguna cuestión. Lo podéis hacer en inglés o en español.
When you spoke about the multigrid problem in the slide 21, is there any practical limit of how coarser can you make the grid?
Well, I think it's not a good idea use a lot of grids. Well, I don't know, but I suppose that it's not a good idea to use a lot of grids. Firstly, because you have to store all that grids. You have to calculate matrices for that grids. And you probably will lose a lot of time going down and up. And after all, you decrease number of elements, so you decrease size of, increase size of step 2 times for each grid. It means that number of grids will be logarithm, so if you will go until the simplest one, will be logarithm of initial size of grid. And logarithm actually is very small. So it means that even for million, for example, well, logarithm basically is number of digits. And so probably you can use 3 or 4 grids. And
Okay, thank you.
¿Una pregunta más o una duda, algún comentario? Bueno, pues entonces antes de agradecerle de nuevo, recuerdo que ahora tenemos un pequeño picoteo que está... una parte lo paga el Instituto de Gregorio Millán Barroani y la otra, os recuerdo como siempre, que lo pagamos entre todos. La aportación es €1 para las pizzas. Y de nuevo, este cuatrimestre ya lo tenemos completo y tenemos algunas para el siguiente, pero si alguien quiere dar una charla, no habláis con nosotros o nos mandáis un correo, ¿vale? Así que nada, pues Sergei, muchísimas gracias por preparar esta charla.